I'm Maddie Krischer, and I'm an undergrad student at Eckerd College. I'm a marine geophysics and computer science major.
We're gonna have a time going here for you, and we'll give you a 2-minute warning if you're coming up towards the end of that 15 minutes. And we're ready to go whenever you are.
All ready? All right, we're ready. Hi, my name is Christopher Darcy. I am the Chief Executive Officer of Phoenix Robotics. This is my 4th year as part of the company. Here at Phoenix Robotics, this is a 9-man crew where we strive to make the products for that meet our customers' demands. Here we have a motto at Phoenix Robotics: soaring to new heights with cutting-edge new technology. Here at Phoenix Robotics, we have several departments, such as the ROV department, the vertical profiler department, the marketing department, and the safety department. I will now hand it off to Ivana, who will talk about our most important department, safety.
Good morning. My name is Ivana Betancourt, and this is my first year in Phoenix Robotics. As the Chief Safety Officer, safety is a big part of my work. Therefore, in Phoenix Robotics, we apply safety in many different ways, such as our safety with our members, with things such as tied her back, rolled up sleeves, and closed-toe shoes. We also apply safety in our facilities with our personal protective equipment, also known as PPE, which are things such as safety goggles and gloves when handling tools. Last but not least, we also apply safety in our robot. As you can see here, we signal pinch points on our claws with a red electrical tape. We have skis under our robot, which let us not damage the bottom of our robot. We also have tether relief, so there's no tension in the robot. We have round edges, so when we move the robot around, we don't get hurt or anything. We also have the gripping handle, so the movement of the robot is easier. And we have the viewing window on top of the robot, so we know if there's any leakage. Talking about leakage, we also have the emergency stop switch, which is in case of any electrical problems or leakage, we can stop the robot and yeah, sorry. Now I'll pass it to Janique, who's going to talk about the theme of our competition.
Hi, my name is Janique. I'm the Chief Marketing Officer, and this is my 2nd year here at Phoenix Robotics. This year, ROV has modeled their competition and tasks after the goals of the United Nations Decade of Action for Cryospheric Sciences. These goals include mitigating invasive species, using technology to preserve underwater platforms, and stopping accelerated ice melts and glaciers. For example, in Task 2.2, Iceberg Tracking, competitors are asked to capture 5 different faces of an iceberg, measure the kill depth, and assess the risk to offshore platforms. This task requires the use of the ROV's complex camera system. Similarly, in Task 2.1, Mitigating Invasive Species, teams are asked to identify the species of a specific crab and decide whether it's invasive or not. Task 2.5 and 3.1 both address the issue of using technology to preserve underwater platforms. In Task 2.5, by removing the biofilm from a Harleywood subsea observatory, you're protecting the ecosystem from any harmful bacteria or pathogens that may kill the marine life there. Now, Ivana will go on to talk about
offshore energy production platforms. Thank you, Janique. My name is Ivana Fumayor. This is my first year being part of the Robotic Phoenix team, and I'm the marketing assistant. So, as we all know, and as my teammate Janique previously mentioned, this year's competition has been centered around what can we do to help stop the melting of ice glaciers. Well, for instance, there are multiple reasons and causes that contribute to this problematic. For example, there's oil spills, chemical leaks, underwater noise pollution, all of which we know are disruptive to the marine ecosystem, damaging coral reefs and altering entire ecosystems. So, in this year's competition, we've been challenged to find more sustainable alternatives to replace these traditional offshore platforms. The reason why this is such a major challenge and problematic is because these energy production platforms are essential to meet global energy demands. So, for example, during Task 3, our team is asked to install a micropile to help secure the wind turbines and help with the installation of it per se. We have, for example, the claws, which has magnets on it that help us with this task, and we also have the camera system that help guide the ROV throughout the task. Now I'll be passing on to Timothy so that he can talk more in depth about the frame.
Hello everybody, my name is Timothy Chow. It's my first year at Phoenix Robotics and I'm the Chief Operations Officer. We decided to diverge away from the normal materials for making a frame. Instead of using aluminum or acrylic, we decided to use some high-density polyethylene and PVC. The reason we use these is not only are they quite available for us, but they're very light, and that's one of our main goals here. The tasks this year are all about surveying around certain tasks, such as getting a full view of the iceberg and getting a 3D model of the coral garden. And it's all about mobility. all about how fast can you do this and how good and how accurate can you do it. So we decided that we need a good ROV that gives us the best mobility and the best precision possible. As we move more into the frame, into the onboard system, you will find a 3.75-inch transparent PVC piece around a 4-inch PVC pipe with cutouts in it so that we can have viewing points of the onboard on shore. In the back, there's a 4-inch PVC cap that has been glued on and has holes in it for the wires. It has been JB welded and has 5200 and epoxy resin. This makes sure that no water can go in, and on top of that, we have a tether release system with a U-bolt and 2 hose clamps and 2 carabiners so that the tension between the tether, which sends all our information, it will not damage any of the wiring inside the onboard. Finally, we have our buoyancy. Buoyancy is how something sinks or floats in the water. And to increase our buoyancy so that we float more, we use this low density foam or high density foam. What this does is that we have a perfect static buoyancy that we always stay at, and when we need to adjust mid-run, we use a double action pump so that we can inflate and deflate air out of our ROV. This gives us the perfect balance between sinking, floating, or perfectly neutral. Now I'll give it on to Chris, who will talk about electronics.
Our ROV's electronics composes of the onboard electronics and the control box electronics. On our ROV and our onboard, we have 4 Blue Robotics T200 thrusters. You may be asking, why did we choose these thrusters? So in our labs, we did research using the Bowler test, where we can put our thrusters in the water and test how much force they accumulate at full voltage. So we used Blue Robotics T100 thrusters and the T200 thrusters to figure out what we would like. And from our research and our many various tests, we chose the T200 thrusters because they're more powerful and they will allow us to move more swiftly in the water to complete tasks faster. In our onboard electronics, we have four Blue Robotics ESCs or electronic speed controllers, that way we can control the speed of the thrusters. We also have a Arduino Uno and a voltage regulator, and they're set down to 5 volts. So our Arduino Uno communicates with our ESCs to our thrusters to send signals, but we can't control it from down here. So we have an ESP32 on inside our control box, which is basically like an Arduino, but it houses a CPU to use Bluetooth and Wi-Fi connection. So with that, we have a more user-friendly interface. By creating our own software, we're able to wirelessly connect an Xbox controller to the ESP32 to send in inputs in there, which then gets sent down 2 wires in the tether to the Arduino, which then gets sent to the thruster to give those commands. We purchased the Xbox controller because we know that coming from a factory like Xbox, and all of us, we like to game, we know that of course this works, and we have a lot of experience using this controller. Also, in our control box, we have 2 MBD 10A Cytrons and an Arduino Mega. This is used so we can control our claws, because on our claws we have 4 25 kg servos, so that way we can do an open and close motion and a rotating motion for each task. So we use this controller with joysticks. So each joystick is for each claw. So this is for the left claw and this is for the right claw. So that way we send inputs into the Arduino, which then sends it to the Cytron, which then sends it down the tether. Now, I would like to hand it off to Coda, who will talk about our cameras.
Hi, my name is Coda Schrader. This is my first year at Phoenix Robotics, and I'm the Chief Technical Officer. This year we put a lot of emphasis onto upgrading our camera system. We decided to have a combination of digital and analog cameras because the missions this year call for that. To start off, the digital cameras give high quality images and have no warp in them. This allows for easy 3D modeling and measuring for the Coral Garden and iceberg missions. Since you only have a 5 centimeter leeway to be able to measure these for full points, you need a really good image, which is exactly what the digital cameras on a robot can do. You can see it right here. Next up, the analog cameras that we are using. They are cheap and efficient, using less amps than the digital camera that we are using. This allows us to put 4 in our robot, 3 in the front and 1 on the bottom for the transect. Because we're able to do all this, we can see all the missions at most angles that we want them to, while also being able to be a backup for 3D modeling and measuring, because in our camera box we have an analog to digital converter. For a more in-depth look at how the electronics are wired, the analog camera is a 50-foot long endoscope that we waterproofed with 5200 and marine sealant that goes through the tether and to this camera box. It connects to this D-Link computer in here that we can manipulate any images we get using this monitor, keyboard, and mouse. The analog cameras go down the tether just like the digital camera, but connect directly to these 3 monitors. This third monitor is able to swap between 2 of the cameras, allowing us to see any of the analog cameras whenever we need to. And overall, we've discovered that using a combination of these allows us to combine usability with efficiency for the best ROV this year. I would like to pass it off to Pranav to talk about flaws.
Thank you, Kodo. Hello everyone, my name is Pranav Kumasirimala and this is my first year in Phoenix Robotics. My role is to work on our cross systems from field. And a problem which we had during previous years is that certain screws over here get too loose, which we dismantle during our runs. This required daily maintenance, which wasted valuable time, and it was also a pain for us. So Desiree and I collaborated to find the solution. We kept the claw design because of its versatility in prop, like taking the collars to poolside, and also we tested other designs, and this is the best design we found so far. We use forces to distribute the force around the screws to make it not too tight or too loose, so we can quickly grip onto tasks like the Hubsy Observatory bipod. Because of implementing this solution, this helped to keep our system well intact and helped us give time to practice in the pool. So because of this helped us to finish making a strong, durable 3-prong claw. I would like to pass it off to Anthony to talk about the profile.
Thank you so much. Hello, my name is Anthony Lozano, and this is my second year as a part of Phoenix Robotics. I am the vertical profiler assistant and worked alongside Desiree to create our vertical flow for this year's competition. I mainly contributed by creating the frame design and the buoyancy engine for this year's competition. And the frame, as you can see, is a frame used from 2 years ago that has been repurposed and perfectly fit for our buoyancy engine electronics. The reason for doing so is because it had the proper dimensions and gave us enough space to reach inside and manipulate as needed. Starting at the top here, we have a 4-inch dome piece with our Baro 2 sensor in the center of it, connected to our I2C converter on the inside. Lower down is our 4-inch acrylic tube that has our buoyancy engine and water valve for easy water access. In the center, we have here our rubber gasket that allows us to pull off and enter either of these tubes if necessary. Lower down, we have our 4-inch PVC pipe that contains our button, electronics, weights, and pressure valve. Onto the buoyancy engine. The buoyancy engine itself is a lead screw design with a 100cc syringe. It also uses a 100 RPM 12-volt motor, which is different from previous years, as we use servos to do this so instead, which were inconsistent and did not work well when we were doing our cycling. We did our research and we found that these motors were more consistent and worked better than the servos, so we inputted this. This is all bolted down onto an acrylic piece that is wedged with a wood board to keep it stability. I will hand it over to Desiree to talk about our electronics.
Hello, my name is Desiree Gardner. This is my first year at Phoenix Robotics. I'm the profile specialist for my team. And while I did work on the ROV quads with Pranav, I mainly collaborated with Anthony to work on the profiler. More specifically, I worked on the electronics of the profiler. The profiler this year uses a modular electronic system that includes an ESP32 board, a MDD 10A Cytron, a I2C converter, a Baro 2 sensor, a 12-volt battery pack, an SD card reader, and a voltage regulator. All these parts were used because they have a different function when it comes to completing task 4, mate floats under the ice. ESP32 is sort of the main part. It's like the brain, and it has 2 functions. The first one is it helps with our buoyancy engine. Then the ESP32 talks to the MDD 10A Cytron, telling it when to switch the polarity of the motor or change the direction, and also it helps the Cytron control the speed and timing of the motor to get the profiler moving in the water. The ESP32 also works with the I2C and Baro 2 sensor. The I2C and Baro 2 sensor to store and collect data while the profiler is cycling in the water. Then when the profiler returns to the surface, the ESP32 tells the Cytron to make a wireless connection to connect with our own software in the form of a web serial. This is so that the profiler can give us the data in a way that's easy for us to read and graph. The profiler system this year is modular, so that the electronics can all fit in one small compartment in the middle of the profiler, with Velcro on the battery pack and the ESP32 board for easy removal and replacement if anything were to happen to the electronics. I will now pass it back to Chris to give our concluding thoughts.
We would like to thank our sponsors and our mentors for continuing to fund us and guide us throughout the year so that way we were able to make it here. We'd also love to thank our parents for dealing with us and transporting us to our facilities when needed. We would also like to give a big thanks to Mate for allowing us to compete in this competition because this competition really changes people's lives.
Very good. Very good. You got some questions?
Yes.
Okay. So, you know, what, first of all, is this able to perform all the tasks?
Yes.
Okay, good. What, if you could tell me, anybody, what was the biggest challenge? What was the one that just really drove you guys nuts and you really had to, you know, work together? Sounds like you're ready.
It took me 2 full days of practice, and I mean like 4 hours every day to fully get down the transect, because the problem with the transect is that when we have a light ROV, it's really easy to move, right? And that's a double-edged sword. Most of the time, it's really great because we can do tasks really fast, we can get extra points, but there is the problem with the transect. The entire point of the transect is to stay still, right? And that's really difficult, especially because we just had to make we just repositioned a camera to look down for that transect. So I thought, okay, this will be easy because we have a down camera now. But it was quite a challenge where I had to get the perfect buoyancy while also repositioning it into the square. Because even if I go a little too far out, it won't count, and if I go too far in, it won't count.
Gotcha. Can we approach?
Yes, yes.
Take a look. So who was describing to me the clause right here? Explain to me again about how the challenges you had with this.
The challenges we had was certain screws like these would get through loose, which would dismantle during our learning, which then we can't operate during the water, and then made us do daily maintenance. So what I did was added lock nuts on the bottom, which can then secure the screw. So instead of keep on adding washers, screwing it in every single time, it can stay put, and we didn't even need to do daily maintenance a lot on screws.
Very good. Very good. You guys have any more questions?
I think so.
All right. Well, y'all did a good job. I was here last year. I really like seeing some of the growth in y'all's in the presentation that y'all do. I can tell you're a little more comfortable in year 2 than some of y'all might have been in year 1. But good job. Okay.